Hi everybody, my name is Francesco D'Amore. I'm a PhD student at Université Côte d'Azur and I work for INRIA in the team COT. I'm going to present our work Search via Parallel Lévy Walks on Zeta 2 together with Andrea Clementi, Giorgia Copis and Emanuele Natale. First of all, what are Lévy walks? So a Lévy walk is just a random walk whose step length density distribution is proportional to a power law with some previously fixed exponent alpha greater than 1. That is, for each positive real number d, the density distribution associated to d is proportional to 1 over d to the power of alpha. On the top left we see a Lévy walk with exponent 2.5. On the top right, the well-known Brownian motion. The speed of the walk is constant, but actually here we assume it to be equal to 1. That is, a walker covers distance 1 in a time unit. Why do we choose to study Lévy walks? Because they have been used to model movement patterns in many species, ranging from bacteria and fishes to ants and mollusks, and also have been employed in the foraging theory. That is the theory that studies how animals search for food. There is an important work appeared in Nature 1999 by Viswanathan et al. That studies some setting, and they prove that Lévy walk with exponent alpha equal to 2 is optimal in any dimension in the Euclidean space, in the sense that a walker maximizes the expected food discovery rate. And also Lévy walk have been investigated in many other search problems and have been proved to be optimal in a wide range of settings. This has led to the formulation of an evolutionary hypothesis known by the name Lévy flight foraging hypothesis, that says that since Lévy flights or Lévy walks optimize random searches, then biological organisms must have evolved to exploit Lévy flights or Lévy walks. Just to mention what a Lévy flight is just a Lévy walk in which each jump is performed in a time unit, so not in constant time. This has shaped much of subsequent research, and we chose to focus on one search problem, the ants problem, which is a known problem in the distributed computing community. It was first introduced by Fannerman et al. In PODC 2012, in which we have k-independent walkers that start moving in the infinite two-dimensional grid from the origin. They move one edge each time unit. There is synchronous time, and there is also one special node, P, that is the target, which is placed by an adversary at a known Manhattan distance L from the origin. The task, of course, will be to find the target as fast as possible. Fannerman et al. Prove a lower bound that says that for any number of agents k for any search algorithm, the hitting time to find the treasure, the target, is at least L square over k plus n, both with constant probability and in expectation. I will not go into details because for the sake of the presentation and for the limited time. And Fannerman and Corman, in the journal version of the work introducing the ants problem, propose many solutions to this problem in many different settings. In one setting, agents exchange information, in another receive some advice. But also they focus on the setting in which there is no communication and no advice. We focus on the latter, also because we wanted to study k-parallel independent Lévy walks, but also because in swarm intelligence it is an hypothesis which is assumed because it maximizes the potential for scalability in such problems. The best algorithm given by Fannerman and Corman achieves expected hitting time, that is L square over k plus L times log to the power of 1 plus epsilon L of L. This log exceeds the known lower bound, but it's tight in the sense that they prove that just log, so with the power of 1, can't be reached in such setting. Epsilon here is a constant that can be made as small as we want. However, the proposed algorithm is not that natural, which is why they also propose a more natural algorithm, the harmonic search algorithm, which uses power law distributions, worsens performance, but also increases probability of to find the target within the stated time. In particular, if we fix two constants delta and epsilon, we want them to be as small as possible. And then for all target distances L that are at most k to the power of 1 over delta, so there is this constraint on the target distance, then with probability 1 minus epsilon, the heating time is at most L to the power of 2 plus delta over k plus L. So you see we have this polynomial value L to the delta that exceeds the lower bound. Delta, we want delta as small as possible, but we can't choose it equal to 0 because the harmonic search algorithm works as follows. Each agent samples a jump length d with a power law distribution with exponent alpha equal 1 plus delta. There is no probability distribution corresponding to alpha equal to 1, so delta must be positive. Then it moves to a destination at distance d chosen uniformly at random and starts a spiral search for about d to the power of delta plus 2 steps, like in the picture. Then it returns to the origin and repeats. What do? To the best of our knowledge, we give the first analysis of the heating time distribution of k-parallel Lévy walks in the grid. We also show how they can be employed to give a very natural, almost optimal solution to the ants problem in the case of no advice, no communication. We start with the definition of the discrete Lévy walk. So we fix a jump length distribution in the following way. D equal to 0 is chosen with probability 1/2. Instead, any positive natural number d is chosen with probability c alpha over d to the power of alpha. Alpha is previously fixed, here it is a constant, but actually for our result it is not necessarily a constant. So after having sampled a distance d with this distribution, the walker chooses a destination uniformly at random at distance d, goes there approximating the line segment, the straight line segment, and then repeats. Now we go for the analysis. Depending on the value of alpha, the Lévy walk exhibits different behaviors. So when alpha is between 1 and 2, we have the ballistic diffusion. Figures A and B show it, in which very long jumps are preferred. Then when alpha is between 2 and 3, we have some super diffusion, in which the walker alternates long jumps and local search. When alpha is at least 3, we have normal diffusion. It is almost all local search, and it is very similar to the non-Brownian motion. The reason behind it is because of the first and the second moment of the jump length. So when alpha is between 1 and 2, both of them are unbounded. When alpha is at least 3, both of them are bounded. When alpha is between 2 and 3, the first moment, the expectation is bounded, and instead the variance is unbounded. We will see this intermediate case turns out to be optimal in our problem. We divide the values of k and L in 3 possible cases. The case of a nearby target, when L is at most k over polylog k. The main case is when L is between k over polylog k and some exponential function in k, and then the case of an exponentially far target when L is at least some exponential function in k. So in the case of a nearby target, actually the best strategy to adopt is the ballistic walk, and any alpha in the interval 1, 2 is good. In this case, with a probability in L that is at least 1 minus 1 over some polynomial in L, the heating time is at most L times some polylog of L. In the case of an exponentially far target, actually we can just choose an alpha that is at least 3 and have a diffusive walk, which is very similar to a Brownian motion. The process is recurrent, then with probability 1 the walks will eventually find the target. But we also remark that if we choose alpha that is less than 3 by constant, then with the probability the target is not found at all. Let's now look for the main case. Here the best strategy, well, it depends. Let's choose this special value of alpha that is 3 minus log k over log L. It's in the super diffusive range most of the times. And we prove the followings with a probability in L. If alpha is alpha star plus this value that goes to 0 as log log L over log L, the heating time matches the lower bound except for a polylog L factor. If alpha instead is greater than alpha star by a constant, actually the heating time is worse than the lower bound by at least a polynomial value in L. If alpha is less than alpha star by a constant, then the heating time is unbounded. But how can we employ this result? Because we do not know K and L, or at least the agents do not know them. Actually, we don't have to find alpha star. Consider the following algorithm. Each agent U samples uniformly at random a real number alpha U in the interval 2, 3, and then it performs a Lévy walk with exponent alpha U independently of the others. And then you see, if we respect this constraint, then the heating time is still at most L squared over K plus L times polylog of L with a probability. When we compare this result to that of the harmonic search algorithm, we see that the lower bound is matched up to this polylog factor here in our case, when instead the harmonic search algorithm had a polynomial value worse, was a polynomial value worse. Also the probability here is constant, here instead we have with high probability. And the constraint of L is also better. We allow L to be at most an exponential function in K. Here it was at most polynomial. The idea behind the algorithm is the following. So if we fix some epsilon that goes to 0 as log log L over log L, and we take the constraint on L plus the Chernoff bound, we have that at least order of epsilon K agents choose an exponent in this range, alpha star minus epsilon, alpha star plus epsilon with high probability, and actually this number of agents turns out to be enough to use the previous result to ensure high probability to find the target fast enough. So we have analyzed the heating time of K-parallel Lévy walks. We have shown this almost optimal search strategy for the ANS problem, which is very natural and improved the harmonic search algorithm. We also argued the non-universal optimality of exponent alpha equal to 2 that previously was turned out to be optimal in a wide range of research problems. In our case, we instead have more of a special range rather than a special exponent. How do we find alpha star? We actually analyze a single Lévy flight, which is a Markov chain. Then we derive bounds for a single Lévy walk through a coupling argument. And then we exploit independence to get results for the K walks. Let's analyze a single Lévy flight here. I remark that I will not show why other values for alpha are worse than alpha star. I just show how to find alpha star. So zeta U of t is just a random variable counting the number of visits to node U within time t. E of t is a conditional event that is necessary for the coupling argument between Lévy flight and Lévy walks. A of t is the number of visits to the origin in expectation within time t. P is the target node, and P of t is the seeked probability, so the probability to find the target within time t. We prove the following. This P of t is at least the number of visits to the treasure in expectation within time t divided by the number of visits to the origin in expectation within time t. So we have to look for these two values. How do we do it? We partition the space in three different areas. The first one, A1, is just a square on whose border the target is located on. So we remember the target is the distant cell. A2 is a ball, which is a rhombus in zeta 2 of radius L polylog L. A3 is what is left. And we prove the followings. We bound the total number of visits in each of these three sets for A1 and for a time that is equal to L to the power of alpha minus 1. We have the number of visits to A1 in expectation is at most a fraction of the total time, a constant fraction. As for A3, we have that the total number of visits is at most t over log t. And we actually prove a very nice monotonicity property, which says that for each node in A1, the Lévy flight has more probability to be on it than compared to each other node in A2. And so the target is more likely to be visited than A2, and the number of visits to A2 are at most the number of visits to the target times the number of nodes in A2. And since A1, A2 and A3 form a partition of zeta 2, and clearly the number of visits within time t in all of these three regions is t, if we substitute everything we have found, we get that the number of visits to the treasure is at least 1 over L to the power of 3 minus alpha times polylog L. This was the reminder. We need to find A of t. Actually, through a difficult argument, we prove that it is constant with respect to the time, and so the probability to find the target within this given time is actually 1 over L to the power of 3 minus alpha times polylog L. And this also for the Lévy walk through the coupling result. For the parallel search, we exploit independence. Since we have this probability for one walker, we just set k to be log L times the inverse of this probability, and then we have k walkers, and the probability to find the target actually is, with some calculations, 1 minus 1 over L. And we have that k walkers find the target within time t, that is L to the power of alpha minus 1 with high probability. But of course we can't fix k, which is given. We can choose k as we want. How do? We actually choose alpha, such that this relation is satisfied, and it turns out that the best alpha is this one, from which we extract alpha star in the first part. Thank you for your attention. Any question will be welcomed in the conference.